As we discussed last time, the forward difference, the backward difference and the central difference formula, all three of them are actually approximations to the exact formula for the derivative, which involves taking a limit as h goes to 0. And if you really could take a limit as h goes to 0 of each one of these three expressions, you would get exactly f prime x. However, on a computer, at least on a computer which uses numerical methods, all we can do is take numerical values. We cannot really calculate a limit, and so we replace h by a small value instead of taking the limit as h goes to 0. And as we have already seen in the last lecture, if we take the limit as h goes to 0, the forward difference and backward difference formula, both of them do reasonably well. The central difference formula, however, does much better. The error between the exact value and the approximation that we have calculated using these formulae actually is much less for the central difference formula. In this lecture, we will try to understand why. We of course also expect that the approximations will become better and better as h decreases. So let's go on to the theory behind it. The theory here essentially boils down to the theory of Taylor series. Notice that f of x plus h, the quantity that we used in the forward difference and the central difference formula, is given by this fx plus h f prime x, and I have written down a few more terms in the Taylor series. The second derivative term with h square by 2 factorial, the third derivative times h cube by 3 factorial, and so on. So of course, if I just truncate the series here, I am incurring an error of the order h square. So you get f of x plus h is f of x plus h f prime x plus a term, an error term because I am dropping it, of order h square. So if I rearrange this, I can easily see that f prime x is actually f of x plus h minus f of x divided by h plus a term of order h. This was order h square, but since I have divided by h to get to this formula, this has become order h. So we expect an error using notice that f of x plus h minus f of x by h is exactly the forward difference formula. So if we approximate the derivative by the forward difference approximation, we expect this term to represent the error, and the error should be proportional to h. And so if I cut down h by a factor of 10, the error goes down, of course, but only by a factor of 10. Now backward difference, you can easily convince yourself, has a very similar behavior. To get to backward difference, all you need to do is write f of x minus h here, which of course involves changing the sign of h here, in all the odd terms. Of course the even terms stay the same, and a very similar calculation will tell you exactly that the backward difference formula is also an approximation of the same order, that is, it also has an error of the order h. Now what about the central difference formula? Well, for this, let's write down both f of x plus h and f of x minus h. These are the two things which go in to calculate the central difference. Now if you subtract these two, notice not only does fx go away, but this h square term also goes away. So the difference actually starts only at the h cube term, right? So this is the first term beyond what we have here, f prime x. And so if we rearrange this, of course we have to divide by this 2h, so this order h cube term becomes order h square. So this is why the error in the central difference formula is of the order h square, so it's a lot smaller for the same small value of h than the error for the forward or the backward difference approximations. And more importantly, if I reduce h by a factor of 10, the error will reduce by a factor of 100. So central difference is bound to be better. Can we do any better than this? Well, we can. Just write down the central difference formula once, then do it again, but now use 2h instead of h. So of course here instead of 2h you get 4h, instead of h cube you get h cubed by 3, and of course there is an order h to the 5 correction. Notice that here earlier we had lumped this under an order h cube error, but here we have deliberately written down what this term is. This is h cube by 3, this is h cube by 3 here. Now you may have already guessed where we are going with this. If I multiply this first equation by 8, it will give me 16h f prime x here, and subtract this term, I will exactly be able to cancel out the h cube term. So that is, I can eliminate the f triple prime x term which has h cube as a factor, and the difference will give me 12h f prime x plus an error, but an error not of the order h cube because that is already cancelled away, but an error of the order h to the 5. Rearrange this and you get a formula for f prime which involves f of x plus h, f of x minus h, f of x plus 2h, f of x minus 2h. To get the derivative at the point x, you need the value of the values of the function 2 steps to the right, up to 2 steps to the right, and up to 2 steps to the left. And this has a much lower error, an error of order h to the 4. Of course, I will have to point out that this extra accuracy comes at the expense of having to do a more complicated calculation, right? So, and also the other shortcoming of course is that here the very first two x values will not have a derivative, the last two will not have a derivative, because those 2 points will not have sufficiently many points either to the left or to the right to calculate derivative from this formula. So if you are willing to drop 4 x values from your array, you can of course use this formula and get a more accurate, albeit more complicated approximation for the first derivative.